A very good morning to all of you. We are moving on to the second day of the International Recent Trends in Photonics, NPS 2021. We begin today's program with an invited talk by Professor Arvinder Sandhu from the University of Arizona. I would like to invite Dr. A. Mujib, Professor, International School of Photonics, QSAT, to invite the speaker.
Thank you, Lakshmi. I'm very happy to introduce Professor Arvind Sandhu to the second day of international conference at ISP, International School of Photonics at Cochin University of Science and Technology. Professor Arvinder Sandhu is the Professor of Physics and Optical Sciences at the University of Arizona. He completed his PhD in the year 2005 from TFR, Tata Institute of Fundamental Research, Mumbai. The research group of Professor Arvinder is geared towards the new applications of attosecond spectroscopy to address questions in the areas of atomic and molecular physics, chemical physics, and nanomaterials. The recent research projects of the group focus on the generation and application of high-flux attosecond X-ray pulses, study of charge migration and coupled electronuclear dynamics in molecules, electronic wave packet dynamics and decoherence, control of electronic processes with laser fields, and exciton dynamics and electron correlations in two-dimensional materials. Professor Sandhu has a list of awards to his credit, including Distinguished Scholar Award from University of Arizona in 2017, Career Award from National Science Foundation in 2010, Excellence in Undergraduate Physics Teaching from University of Arizona in 2010, and other includes the Young Scientist Medal from International Science Academy in 2007. With these words, I'm very happy to invite Professor Sandhu for the talk. Please, Professor Sandhu.
Thank you, Professor Mujib, for the introduction. It's an honor to be here. And thank you, Professor Gopinath, for the invitation. I see that you guys have a great program, and I'm sure you have a very ambitious and motivated bunch of students. So I'm going to give a talk which is mostly, it's kind of at a level which will start out very basic. So, but if it gets a little bit involved, please don't hesitate to stop me, and I'll be happy to to go into details. So I guess I need to share my screen if I have your permission to go and do that.
Yes, please.
Okay. All right. So, all right. So I think you should be able to see my screen now.
Yes, it is visible.
All right. Perfect. So as the title says, I'm going to talk about electronic processes that we want to probe using attosecond pulses. And as Professor Mujib already told you guys, I'm from Arizona, and I've been there for now about 13 years or so, 13, 14 years. So the first slide basically introduces the concept of ultra-fast science, which I'm sure you guys are very familiar, but I feel like, it's a good way to start the discussion here. So I have different times durations on the x-axis in three orders of magnitude. And they go from 1 second all the way down to a nanosecond, picosecond, femtosecond, and so on. So I'll use a laser pointer now. So let me set things up a little bit better. Okay, so beyond femtosecond, which is 10 to the minus 15 second, is 1 attosecond, which is 10 to the power minus 18 seconds. And just to give you an idea that the ratio between 1 second to 1 attosecond is same as ratio between 1 second to age of the universe, or even more than that. So if I extend the arrow on the other side and I have the same length arrow on this scale, then I would exceed the age of the universe. So it's a very small duration. 1 attosecond is a very small duration. And you guys know that we observe different phenomena on different time scales, and we use different detectors to do that. So if you want to see something on fraction of a second level, you can use your eye. It's a very good detector, actually. But if you want to resolve phenomena on millisecond level, you have to use very fast shutters, maybe electronic shutters or mechanical shutters. And I think you guys are familiar with this picture where Edward Muybridge demonstrated that using a fast camera, he could take a picture of a horse in the mid-gallop with all the 4 hooves off the ground. If you want to go beyond that, you have to get very creative with your shutters, and you may use some kind of electromagnetic shutters. And this is a picture of a nuclear explosion, which was taken by Harold Edgar Turn from MIT, using a fast shutter. Now, another way to capture fast phenomena is to use a strobe light, where you keep everything dark, but you shine a strobe light for a very brief duration, for a brief instant, during which you capture the motion, right? So, so it turns out that these electrical and mechanical techniques don't work if you want to strobe the phenomena below a microsecond. Let's say if you want to go to nanoseconds or picoseconds, where we enter the quantum regime, which is what you guys are interested in at your institution, and we are interested in. We want to study these dynamics of these quantum objects, rotations, vibrations. To do that, you have to use laser as a strobe light, because lasers allow us to produce very short pulses of light because they are coherent, and you can have a lot of colors in phase, and then you can compact that into a short pulse. So so that has been possible since, a little bit after the invention of the laser, people quickly learned how to make femtosecond pulses, and they became a commonplace in 1990s. You can commercially buy these femtosecond amplifiers, as you have many of these things. But if you want to go below a femtosecond, it becomes a little tricky. The amount of bandwidth needed becomes very large. So we have to go to the XUV regime, and I will explain why in a little bit. But using these XUV pulses from which we produce in our lab, we can get down to attosecond time durations. And then you can probe not just atomic dynamics, but you can resolve electron dynamics, which are occurring on a much faster time scale than the motion of atoms or nuclei. Right? Electrons are lighter, so they move faster. Now, you may ask a question, and you probably know the answer. Why do we do this? Why do we want to look at these ultra-fast phenomena? Well, the answer is that they have implications for real life. So if your eye is a detector and it's sensing some phenomena, then it works based on some photochemical reactions. And to understand those photochemical reactions, for example, the isomerization of rhodopsin, which leads to the first step in vision, you need to apply techniques like this because it happens too fast. One of the steps in this isomerization is 50 femtoseconds. So these ultra-fast techniques help us connect to and understand complex phenomena in real life. And not just that, you can use these ultra-fast techniques to control these phenomena as well, at least in the in vitro level. When in a controlled reaction environment, you can control these phenomena. Right. So now to explain why you need XUV or X-rays to produce attosecond pulses, I want to remind you of the Heisenberg uncertainty principle, or a Fourier time bandwidth relationship, which tells us that if you have a very short pulse, you have a very broad spectrum. Okay, if you want 100 attosecond duration pulse, delta t is 100 attosecond, then the delta omega is very large. It's 10 to the 16 hertz. And if you take delta omega by omega, in an optical regime, omega is in EV or so, then the delta omega by omega is 10, which means you have to have a bandwidth which is 10 times more energy content than your central frequency. So that's very hard. But if you go to the X-ray regime, then the omega is very large for X-rays. So delta omega by omega, excuse me, my voice is down because I've been sick with some cold. So I hope you can hear me. So delta omega by omega for the X-rays is very small. It's only 1% of the bandwidth. So as you can see clearly that it's easy to produce 1% bandwidth around some color than 10 times larger bandwidth. So therefore, most often when you try to produce attosecond pulses, you go to very high photon energies. Okay, not just that, if you go to high photon energies, you can get very small wavelengths, which give you excellent spatial resolution as well. So therefore, attosecond and X-rays go hand in hand. You know, they offer dual benefits. Now, people have been using these attosecond X-ray technology in two forms. One is tabletop based, where you have an ultra-fast laser amplifier to produce high harmonics. The other is based on free electron lasers, where you have a kilometer-long path where you accelerate electrons, then you make the electrons wiggle, and the wiggling electrons emit radiation in X-ray region. So you have two different approaches to producing X-rays and attosecond pulses, and they have their own advantages and disadvantages. You know, tabletop setups produce very short pulses compared to the large free electron lasers, but the pulse energy obtained with tabletop sources is much less than those of free electron lasers. Okay, so they're weak sources of very small duration pulses, and also they're more cost effective than with the cost millions of US dollars, or $1 million US, whereas the free electron laser is a huge facility which costs $1 billion. So I will tell you that there are possible ways to bridge this gap and develop some new tools in the middle here. So if I get time, I'll talk to you about one of the projects we are working on in the middle here to capture the benefits of both of these type of sources. But most of the time, I'm going to talk about applications of this technology, which already exists in my lab. So this is how we produce tabletop attosecond high harmonics. We take a femtosecond pulse, we focus it into a gas, and out comes the XUV radiation in the form of attosecond bursts. So it's pretty easy, and it relies on the following physics. It's called a three-step model, which was developed by the people here and implemented by the group here. So the idea is that if you subject an atom to a strong laser field, the Coulomb potential, the 1/r potential, gets distorted, and the electron can tunnel out. So when the electron tunnels out, it can be accelerated by the laser field. And when the laser field changes its direction, because it's a sinusoidal laser field, the electron can come back and recollide with the ion. And this electron recollision is like it's like a Bremsstrahlung radiation. So you end up emitting X-rays, which are very energetic in this process, and also they're coherent because because the entire trajectory is driven by the laser field. All right. So you can produce these X-rays every half of a laser cycle. Okay, you can produce X-rays here. When the laser field goes up and down, you can produce X-rays again. Then the electrons come back again, and you can produce X-rays again. Or XUV or X-rays I use interchangeably. But the thing is that, the one cycle of a laser field is about 2 femtoseconds. So half a cycle is about a femtosecond. So which means that you're producing these X-rays in less than a femtosecond. So each burst is an attosecond burst. Of course, there are many bursts, and you can pick one burst if you work hard, but naturally they come out as multiple bursts of attosecond duration. And they're synchronized to this IR field. And we're going to use this synchronization to do experiments which are pump probe, where XUV pulses will pump something, and the synchronized IR field will be delayed, and it'll probe that process. Okay. So now people have already made a lot of progress in this field, in the attosecond spectroscopy field, by observing various, unique phenomena. People have looked at how much time delay is there when you ionize an electron from different orbitals. What are the relative time delays? Now, this question wasn't asked before. In the quantum textbooks, you don't ask this question. You just say, well, there is energy level E1 and there's energy level E2, which could be in the continuum, and you just make a jump from E1 to E2. You never ask how much time does it take to make the jump. Is the jump from E1 to E2, is it the same time as E1 to E3, or is there a time difference? Now you can answer those questions. You can create electronic wave packets, but because you have such a wide bandwidth now of EVs, you can create electronic wave packets which move very fast in time, which evolve very fast in time, and you can observe the dynamics stemming from this effect. You can also excite inner electrons because you have high photon energy, and then you can look at decay dynamics which occur on attosecond to femtosecond timescales. So there's a lot of applications of these ideas. We are going to focus on only some things. The main emphasis that we are working towards, and what I want to talk about today, is how do we connect this attosecond dynamics, which involve electronic excitation, to a longer term dynamics, which involve the motion of the atoms. And therefore, somehow the energy has to be shared from electrons to the rest of the molecule. So if you excite some electronic probability density on one part of the molecule, then that will get distributed because of electron nuclear couplings, where the electronic energy is given to nuclei and then they're moving, and the whole molecule then can change its structure as a result of that. So that is often what happens in a lot of chemistry and a lot of biology, which is driven by photons. The photons give energy to electrons, and the electrons then distribute the energy to the lattice, to the nuclei, and that's how most processes proceed in life. Okay. But the challenge is connecting the dots, connecting the attosecond steps to the charge transfer and structural dynamic steps which occur on longer timescales. And I'll give you one example which you might have seen, when you were in kindergarten or something. You often had these kind of like tasks where you connect the dots. So this is a picture where the dots are numbered, and if you connect all the dots together, you will see the full picture. Okay, so for example, if you were to actually print this picture and connect the dots, you will see a giraffe here, right? Which is a biological entity. So that is what our goal is. We want to connect the dots from electronic motion to nuclear motion to the entire structure of the molecule, to see what is the impact of this photon on the entire system, right? So to do that, we need to quantify these fundamental couplings between electrons and nuclei, and between electrons and electrons. So that's how we will make progress in understanding and applying the ultrafast tools to real life systems. All right, so let me take 1 second of a break. And again, to remind you that if you have any questions, please don't hesitate to reach out and stop me, okay? Okay, so now I'm going to switch gears to textbook description of what I just said to convey the point again. So I said we want to understand the couplings and correlations, electron-nuclear couplings, on how electrons give energy to nuclei and other degrees of freedom. And quantum mechanically, we can understand that in terms of Hamiltonians and couplings between states. So let's start with the simplest Hamiltonian, which you can diagonalize, okay? And in the process, you can also obtain the eigenfunctions and the eigenenergies, and therefore you can write and the energy dependent phase factors, you can multiply them with the eigenfunctions, and you can obtain a time dependent wave function of the entire system. And the entire exercise is trivial after that. All you have to do is basically assign appropriate amplitudes and then follow the motion of a system in time. So it will rephase and dephase, but most of these dynamics after that is trivial. In real life, the problem is much more complicated. So in terms of what I just described, these states, this diagonalized Hamiltonian is hard to realize because there are, of course, other perturbations or interactions, which could be electrons coupled to nuclear motion, or electrons coupled to other electrons, or electrons coupled to the light fields, or a mix of all this, right? Which leads to very complex dynamics. In one way of thinking about this is that the Hamiltonian develops off-diagonal matrix elements, and the phi ends are no longer the eigenstates of the system. And the problem is that you don't know these off-diagonal couplings a priori. You don't know how strong different couplings are. So therefore, you don't know how to proceed with diagonalization of the Hamiltonian, how to write a time-dependent wave function. You have to experiment. You have to follow the system experimentally and then model it theoretically under some approximations. And that's when you can model your biology and chemistry. So, but if I could experimentally quantify these couplings and give them to a theorist, then task would become easier. So that's what I'm going to talk about. How do you measure these couplings between states using experimental tools that we have developed? Okay, so to give you the overview and to keep an eye on the time, we are going to talk about just one topic. In my lab, we do this problem in different ways. We look at light-induced couplings, and I'll tell you briefly about that in 2 slides. We look at electron-phonon couplings, which is another version of electron-nuclear couplings, except in here we do things in gas phase, here we do things in solids, like for example, in 2-dimensional materials, right? Or you could look at electrons coupling to each other. Also, we are developing some tools which can help us understand these kind of problems which occur on true attosecond timescales. So I won't have time to go through all this. So I'm going to focus on just this topic, and maybe, if I get time, to talk about this new advances. Okay, so let's get to the problem at hand. What is electron-nuclear coupling and how does it manifest? Well, think about it this way. If you plot, I don't know if you're familiar with potential energy curves or not, but simply potential energy surface of a molecule is the energy levels of the molecule for any given internuclear distance. So if you solve for the energy levels of a molecule at a given distance, you obtain some levels. If you change the distance, then you obtain another set of levels. And if you connect all of those dots, you obtain potential energy curve or a surface. So it so happens that if these potential energy surfaces of 2 different electronic states come close together, then our methods of treating this problem quantum mechanically break down. And one way they break down is that often we assume something called Born-Oppenheimer approximation, which assumes that electrons move much faster compared to nuclei. But at this point, where potential energy surfaces come close together, the time scale for electronic transitions increases. Why? Because the energy gap is decreasing. Therefore, if delta E decreases, the delta T increases. If delta T for electrons increases and becomes comparable to nuclear motion timescales, then you can no longer say electrons are slower than the nuclei. So now you cannot treat this system quantum mechanically very well. And these points where you have 2 surfaces touching each other is called a conical intersection. So these conical intersections are the prototypical examples of where the Born-Oppenheimer approximation breaks down, and where we see non-adiabatic dynamics. Okay. So we're going to look for such effects and try to probe them. And these effects are very important, and they are all over in our world. And the photochemistry of vision involves conical intersections, the photocatalytic charge transfer mechanisms, the protection of DNA from UV. When the UV light hits your DNA, these conical intersections help to quickly get rid of the excitation through these couplings between electronic states. And therefore, your DNA survives UV light in many cases. So we are going to try to quantify this, not just observe it, but we're going to try to quantify this. And our approach is to use a ultrafast laser pulse to produce these high harmonics in a gas cell. And then we focus it onto a target gas, and which basically excites electrons. And as the electrons are giving energy to nuclei, we come with the probe pulse and we break up the molecule and we analyze the fragments on a detector called velocity map imaging. Now this allows us to see the movie of the reaction in real time. And that's my goal, in often in these experiments. Okay, so we tried this experiment in a carbon dioxide molecule, and that's what I'm going to talk to you about. And I know that, I'm veering into chemistry now a little bit. So if you bear with me, I will try to keep it very simple. So what we do is we simply remove an electron from the CO2 molecule. If I remove the electron from outer orbital, this is the outer orbital, I get this X state. If I remove the electron from pi orbital, I get this so-called A state, which looks like this. It's a hole in the pi orbital. If I remove an electron from the sigma orbital, which is a more tightly bound orbital, then I get sigma orbital hole, and that corresponds to this B state, which is a higher energy state because it takes more energy to remove an electron from sigma orbital. This A and B states, we forget about all that other chemistry stuff and notations. These A and B states cross each other, and that's where we have our conical intersection. That's where the electrons can give the energy to nuclei, right? So that's a good system to look at. So it turns out that people have analyzed this system theoretically, and they found that it actually is a very interesting system because the electrons couple to the two nuclear motions, the bending of a molecule and the stretching of a molecule. So, so we can look at how this evolves. So we come with our XUV pulse, which is attosecond pulse train, and we create this hole in the sigma orbital, in the B state. And then the electrons give the energy, to nuclei, and you find that after a while, because of the nuclear motion, you end up in the A state, and the hole has gone to the pi orbital. Okay, so this is due to this so-called electron nuclear coupling. Now, if I come later, after 1 femtosecond, after 10 femtosecond, after 100 femtosecond, with an IR probe, and I monitor how much population was left in the B state, I would know what's happening to the electronic excitation, because if it moves away, then my population in the B state goes down, and then when I excite it to the C state, the amount of ions I produce from the C state will go down as well, because the C state breaks up to produce CO plus ions. So this is what we'll monitor in our experiments. We'll monitor the CO plus ions as a function of time delay between the red pulse and the blue pulse. Okay, and this is our data. So focus just on the blue curve here. You see that initially the yield goes up, and then it does seem to oscillate a little bit. Very weak oscillation, but there's an oscillation. So if you subtract this decay, then we see this oscillation more clearly, that there is indeed an oscillation. Okay. Now there are several interesting features about this oscillation. First of all, it's real, and this decay can be explained by the fact that the molecule is rotating, and when it rotates, it becomes less and less likely to be probed. So that's why there is a decay, but it's a real decay. And if you subtract it, you can model it also, you subtract it, you see a real oscillation here. Now this oscillation has an amplitude, its amplitude is decaying, so there's a lot of physics here. So we'll try to process this quickly. All right, so now the goal is, while we get the experimental data processed, we want to learn something about these off-diagonal couplings between the electronic states. Now in our case now, these electronic states are A state and B state. So we have A and B states, and they are coupled by the nuclear motion. And there is two motions, as I said, bending and stretching. So therefore there are two operators. But the end result is that these chi's are no longer the eigenstates. But if you knew these off-diagonal matrix elements, you could do a transformation to the new eigenbasis, which is a diagonal basis. And the elements of that transformation matrix contain a mixing angle called theta when you diagonalize the system. And this theta is simply a ratio between the strength of the coupling and the energy separation. So basically we are going to measure this we're going to model the system, and we're going to try to measure this mixing angle or this coupling strength, right? So I don't want to get into too much detail here, but if you knew the eigenfunctions, you can write a time-dependent wave function, as I already told you before, and then you can model the type of yield you will get, the experimental signal you will get. So you can model it as a DC term and as an oscillatory term, which has oscillation frequency determined by the energy gap between the two states. Okay, so this analytical expression captures the oscillatory part. So what we see in the experiment is an oscillation. If we model it using multi-configurational time-dependent Hartree methods, we see an oscillation, and this oscillation corresponds to the energy gap between the states, and it does match. Experiment and theory match pretty good. So we can measure this E plus and E minus from the experimental data, okay? Which is what you would expect in such a case, right? So makes sense. Moreover, you can also now develop a visualization of this, how this is happening. So this oscillation that we are seeing is essentially, it's not just a measure of energy gap. It is actually telling you where the hole is in which orbital at any given time. When the hole is in sigma orbital, it's very likely to produce CO plus ions. When the hole goes to pi orbital, it's less likely to produce CO plus ions. So this oscillation here corresponds to the electron hole, shown in orange here, going from on axis to off axis pi orbital here. At the same time, the simulations tell us that the nuclear degrees of freedom are excited, and you can see the nuclear wave packet ramping up its motion when the electron is going to the pi orbital. So electrons just don't move by itself. It's the nuclear motion that's causing them to move. Okay, and you can basically do a little more processing, and you can develop a movie of how things are evolving. On the left, you plot the electronic probability density. On the right, you plot the reduced nuclear wave packet density, and you can see that the nuclear motion is mediating the electronic motion, and you can capture both of these essentially by careful experimentation. So now we can answer some questions about the system. If you were to just use a simple model, what you will get is the fact that these oscillations will have some contrast, this amplitude, and this amplitude is a ratio of the second term to the first term. So it's the second term to the first term. And remember, this theta is the mixing angle in our representation transformation. It's the mixing angle which takes us from the vibronic basis to the diagonal basis. So if I measure the amplitude, I know the mixing angle theta, because if I know amplitude C0, I know theta. If I know theta, I know the off-diagonal matrix element, which was our goal. We wanted to quantify these couplings between A and B states. So theoretically, we find a mixing angle. Experimentally, we also can find this mixing angle if we find the amplitude, but the amplitude is changing in time. Well, we can find the amplitude as a function of time and then extrapolate back to time 0, and that will give us the amplitude that can be compared with theory. So we do that, and we find that the experimental mixing angle is comparable to the theoretical mixing angle, which in a sense tells us that now we know the strength of the off-diagonal coupling. Now in this case, the problem was a little more tractable. Theory could tell us what the mixing angle was. In cases where the theory doesn't know the answer, we can still apply this experimental method to obtain some of these answers by using this pump probe spectroscopy. All right, so then you may ask, well, why the theory didn't have any decay in the amplitude and the experiment has? Well, that has to do with the fact that that we have a warm gas. When the gas comes out of a nozzle and we are experimenting with it, it's sitting at some temperature of 200 Kelvin or so. And that implies there are many rotational states that are populated. So when we create our wave packet between the two vibronic states, A and B, we have multiple rotational levels that are simultaneously populated. So as a result, we have a frequency E1 minus E2 for each one of these rotational pairs of levels. Now, if the rotational levels were equally spaced for both, then that would be fine, but they're not. And as a result, you have many different oscillators at many different frequencies, and they dephase in time. And that's what leads to this decay of the amplitude. So we can learn a lot from this simple experiment. And I skipped a lot of details, but the idea is that we can apply these techniques to learn a lot about electron dynamics. All right, so and we model this classically, quasi-classically, by constructing a rigid rotor model, and we found that indeed the decay of the contrast can be obtained, and it matches and the theory also exhibits a similar decay once you allow the rotational levels in the mixture. Okay. So now I'm going to take another break and see if you guys have any questions. If not, I would continue to talk briefly about another topic or two. I think I have time. I have another, I would say 10 minutes or so. So, or maybe 20 minutes.
Yeah, of course, Santhu. You have 20 minutes more.
Excellent.
Yeah.
So I think, excellent. So I can touch upon maybe this topic and a little bit of this topic then. So I just want to tell you guys, I said electronic states can be coupled together by nuclear motion, but electronic states can also be coupled by light itself. This is what happens a lot in our experiments when we work with lasers. And I'll show you one simple example which demonstrates it. So consider an atom like helium. Okay, helium has very discrete energy levels, very well-known structure. Now, if you put this atom in a laser field, let's say 10 to the 11, 10 to the 12 watt per centimeter square, the situation becomes very interesting. So these discrete energy levels, they get modified. So I plot on the x-axis the laser intensity. On the y-axis is the energy of the states. So these states here. So we find that these states up here, these Rydberg states, shift. And these shift because of simply Ponder motive energy, because the electron is oscillating in the presence of a laser field. So you have some cycle averaged energy that gets added onto it. And as you increase the laser intensity, this energy increases, so it gets shifted. But if you consider these electrons which are tightly bound, the problem is more complicated. and the states split. Because of the laser field, there's Stark splitting, AC Stark splitting, and on top of that, you also see light-induced states. Because even though, if you have photons over here, there is no state here, but these photons can still be absorbed because you can do a 2-photon transition to a dark state. 2s is a dark state. So you can do a 1 photon up, another photon down to a dark state, and therefore you absorb your photons here. So you end up seeing a new light-induced state structure in the presence of this red laser field. So the message here is that in the presence of light, the atom is very different compared to the unperturbed atom. So you have to keep that in mind when you use laser fields. And this thing happens, the structure that we calculated here happens because of couplings between different electronic energy levels mediated by the light field. For example, this is a coupling by the red photon between the blue level here, which is a virtual level, and the dark state, which is a 2s state, right? So there are many such examples, and we have looked at them using transient absorption, attosecond transient absorption, where we tune one of the photons near some resonance, and then we try to change this wavelength, and we observe how the coupling changes between the two electronic states and what effect does it have on the line shape of this absorption of this resonance. So I plot this line shape with 2 variables as a function of energy, and as a function of time delay between the blue and this orange pulse. So there is a lot of interesting physics here, which you may have read in your textbook. There is something called Outler-Towns effect. So you can demonstrate that a line here can split because of this resonant interaction, and at time delay 0, you see a splitting of the lines here. But if you change your wavelength, you may alter how this line shape looks. So you can demonstrate that you can go from a Lorentzian to a Fano-like line shape. So by couplings, by tuning these couplings, you can change how your atom absorbs the light. Okay. You can also, do nonlinear physics that you may be doing in your labs and your class, in your, textbooks. You may be reading about second harmonic generation, 4-wave mixing. You can carry on all these concepts to the XUV regime and the attosecond time durations. So here I demonstrate a case where we use tens of EV energy, 27 EV energy, and we are doing 4-wave mixing in the XUV regime. We are producing new emissions here at very high photon energies. So all these are examples of light-induced couplings, which can be processed and to learn something new about how light matter interaction works on short time scales and high photon energies. All right, so again, this is somewhat qualitative, but you can go beyond this and you can start asking questions on how the light fields may impact the natural dynamics of the system. Previously, I gave you this example of a conical intersection where the electron was oscillating between the A state and the B state, and we were tracking this motion, right? But what if I were to put a strong field on a molecule? What happens to this conical intersection? So we see experimentally the signatures of the fact that this oscillation frequency changes and the amplitude changes. So we can control electron dynamics by applying strong fields. Right. So I think that's pretty much what I wanted to talk about in terms of light-induced couplings. It's a very broad topic. You can look up some of our work here if you want. I think in interest of time, I want to tell you about some new developments. Since it's a photonics symposium, I thought I'll talk a little bit about the light. So as I told you earlier, we need bandwidth to produce short pulses, and it's easy to produce this bandwidth in the X-ray regime. So, and I told you there are 2 techniques to do that: tabletop harmonics and the free electron lasers. but they each have disadvantages and advantages. Cost, amount of energy that you can produce. So what if we want, we want to compromise and find something that's maybe not as high of a cost, but more photons, more pulse energy. So that's something that we are working towards. This is just to show you guys. So this free electron laser is indeed quite a monster. There is an accelerator here, there's an injector, undulator here, and you produce the X-rays, and then you work. So this is a kilometer-long tunnel under a highway. So it's very expensive, right? But it's very powerful. You can study proteins and all that. But what if we wanted to do something on tabletop? On tabletop, you can't get to very high photon energies like these free electron lasers. But people have recently demonstrated that if you make the wavelength longer of the laser, and that means the electron can be accelerated more in the laser field, because it has a lot of time now, because the wavelength is very long, so the time period is very long. Then the electron gets a lot of energy, and then if you bring it back, it can produce photons all the way from tens of EVs to hundreds of EVs to even up to keV. So now you can do something which was not previously possible. But the photons are very, very few here. But the spectrum is so broad that you can produce pulses which approach a single attosecond limit. No one has measured them yet, because it's extremely hard to even characterize some pulse which has a bandwidth from 100 eV to 1 keV. So it's a very interesting problem. But anyhow, we are developing this technology in our lab as well. So but because the photons are so weak, we are investing into higher repetition rate so that we can do the experiments. So in my lab, we are buying this high power laser with tens of kilohertz repetition rate, so that we can reliably produce a lot of, not a lot, but 10 times more flux than existing lasers to probe essentially electron dynamics in various systems using X-ray absorption edges. You have carbon absorption edge at 280 eV, you have nitrogen absorption edge at 400 eV, you have oxygen absorption edge at 500 eV. So if you have photons at these absorption edges, you can not only monitor the electron dynamics, you can also tell where is the electron at any given time on which atom, because each atom will have a unique absorption signature. So that's one of our goals that we are pursuing in my lab. But at the same time, I'm also working collaboratively with another group to produce an intermediate solution where we have very, very high photon energies and much higher pulse energies than tabletop lasers at a modest cost, tens of millions. Okay, so this is called compact X-ray free electron laser. And what we do with that is that we essentially replace the magnetic undulator in a free electron laser. So magnetic undulator is basically a set of magnets with alternating poles, and which causes the electron beam to wiggle because of the Lorentz force. And when the electron beam wiggles, it accelerates, and therefore it emits X-ray radiation. But in this case, the undulator period is 3 centimeters. But what if we were to make this on tabletop, this undulator, by using laser light field to undulate the electrons, not the magnets, but the light field. So this process can be done with the laser wavelength, which is roughly a micron. So the undulator now has a period of a micron. If the undulator period is a micron, the X-ray wavelengths that you produce can be much higher for a given electron beam energy. Okay, so this is a neat way of producing X-rays on a tabletop, making your own free electron laser essentially. So this is what we are doing, and it's not like really a tabletop, but it's like 10-meter long free electron laser system, which is being developed at a university like an hour and a half away from me, Arizona State University, and I'm collaborating on the laser part of it and the experimental AMO part of it. So I'm very excited about it. And so I think combined with the technology that we are developing in my lab, which was, based on long wavelength light sources and the compact XFEL that I showed you here, we will have a lot of opportunities to do exciting science where we can probe dynamics of electrons in an elementally specific way. We can take a molecule and we can park our X-rays on nitrogen or carbon absorption edge, and we can monitor if you were to create some excitation or a charge in the valence shell of this molecule. If the charge is on nitrogen, then the absorption of from 1s shell of nitrogen to the valence shells of nitrogen will change. If the charge goes to some other side of the molecule, then you'll get a different absorption. So you can monitor the attosecond motion of the electron through a molecule by using these pump probe techniques. So it's a fascinating prospect. You can extend it to study, how the structure plays a role in the motion of a charge from one place to another. Yeah. You can look at how nanomaterials, how the excitons move between layers or in a layer by by essentially tuning your X-rays to look at either molybdenum absorption or tungsten absorption. You can look at heterostructures. You can look at controlling the catalysis between different metal centers by using X-rays, which are high photon energy and which are targeting, various metals as reporter atoms. You can essentially develop the time domain analogs of all the X-ray spectroscopy techniques that have been developed at synchrotrons. I don't know if you're familiar with these terms. These are, near edge X-ray absorption spectroscopy, extended fine structure, or circular dichroism. You can do a whole lot with X-rays now and with XUV light in a time resolved fashion. So you can develop all these time resolved versions of this. In fact, you can go all the way down to attosecond resolved. You can also do nonlinear Raman processes with X-rays now. At least at FELs, you can do it. You can have enough photons in multiple colors to cause valence excitations using X-ray Raman processes, which was a lofty goal, but now it's being done. So that pretty much brings me to the end of my talk here. I want to basically thank all the folks who did this work. I presented the work which was done by various group members in my lab. Some of them actually have moved to take different positions. And we also have had a lot of theory help from different groups in US and abroad to look into this. And of course, we have had funding agencies, NSF, Army, and the DOE, which have funded our efforts. Now, before I stop here, I want to maybe leave a slide which kind of captured various projects that we are working on to, again, show you some of the references and the work that we have been doing on different problems involving electron nuclear couplings and electronic couplings and light-induced couplings and so on. So with that, thank you so much for your patience and listening to what I had to say. So I'll stop sharing my screen in presentation mode. Okay.
Thank you, Professor Santhu. Okay, let me ask a question in the chat box. There's a question. Can you hear me?
I can hear you. Yes.
Yeah. There's a question. We have discussed the modeling part, right? Will it be possible to include nuclear energy levels also while modeling theoretically? The nuclear energy levels also to be included, can we include? That's the first part. Then if we include that nuclear energy level, what modifications happen in that case is the question.
Right. So the nuclear energy levels typically, the energy spacings are very large. So you have to go to uh, in traditional nuclear physics, you of course end up using megavolts of energies, but there are energy levels which can be addressed using optical means or X-ray means. And I mean, we don't do that, but there are people who are interested in such transitions, and there's nothing preventing including that as a part of the problem if you want to excite your nuclei. So what I meant when I said nuclear dynamics, I meant the translational energy or the vibrations of the nuclei, not the internal nuclear excitations. But in principle, if some problem is there where you have too closely spaced nuclear energy levels, you can cause transitions, and you can include that in your modeling.
Okay, Professor Santhu, could you please elaborate or comment on inverse Compton scattering with laser Wakefield accelerated electrons?
Yes, sure.
Please.
So yeah, so let me go there. And okay, so let me share my screen here again. All right. Okay, so this inverse Compton scattering is actually a very simple process to understand. So as the name suggests, it's a version of a Compton scattering, and Compton scattering involves scattering of a photon of an electron. Now, in this particular case, one way to understand the inverse Compton scattering is that, let's say you have a beam of electrons. Okay, they're coming fine on this way, and they are relativistic. They have very high energy, so the velocity is very high, very close to the speed of light. Now you shoot a laser at this beam of the electrons. Now, if you go to the lab frame of the electrons, let's go to our relativity course, and let's say I do a Lorentz transformation to the lab frame of my electrons, or the rest frames. So these electrons are moving very fast, but I can move to the frame of electrons. Okay. In the frame of electrons, the rest frame of electrons, the laser photons get Doppler shifted to very high energy. So the laser energy, laser wavelength gets divided by a gamma factor. Okay, so the gamma is the relativistic gamma factor. So if gamma for our electron energy, gamma is about 30. Okay, so the electrons see this laser field with much shorter wavelength. Okay, because the laser is coming at it and its frequency is Doppler shifted. So then some of these photons get scattered off the electrons, right? I mean, in any process, there is a probability that the photons will get scattered off the electrons, right? So some photons hit these electrons and then they scatter off. And now let's go back to the lab frame. Okay, so we were in the electrons rest frame, and some photons got scattered, and we know their wavelength. Their wavelength was lambda laser divided by 1 gamma factor, by the gamma factor, so lambda by 30. But we were in the rest frame of the electrons. Now let's get back to the rest frame of the lab, lab frame. And now these photons that were scattered, they will accumulate another gamma factor. So we will divide it by another gamma. So we get gamma squared here. So we had 30 times 30, that becomes 900. So if you had 1 EV radiation, now your wavelength is reduced by gamma squared, or your energy is increased by gamma squared. So 1 EV radiation becomes 900 EV radiation, or close to a kilo electron volt radiation. So as a result of this process of where you give your electron energy to the photons, which is inverse of giving the photon energy to the electrons, here you're giving the electron energy to the photons, and the scattered photons have much higher energy, is the process of inverse Compton scattering. And you go from 1 EV photon energy to roughly 1 keV photon energy, because your wavelength goes from 1 micron to 1 nanometer because of this factor of 1,000 here. Okay, so gamma square is 1,000. So that's how you get to the X-ray wavelengths through this inverse Compton scattering. So I hope that made sense.
Yes. I think due to a restriction of time, let me ask one more, the final questions in this session. Could you please comment on the detection of attosecond pulses of kilo electron volt energy?
Yeah. Well, so as I said, you can have these electrons now all the way up to kilovolts. So how do you detect them? Well, I mean, the detection is, synchrotron people have been working with soft X-rays for decades, so it's all well developed. But nowadays, recently, there has been a lot of improvements in the CCD detectors and in the CMOS detectors, and they work very fast. In fact, you can do this detection directly with your CCD cameras. Of course, they have to be in the vacuum, but you can just put your camera and you can put a grating, and you can disperse this spectrum. This image is taken with a grating and a CCD, and you are integrating here. So basically, each one of these lines could be a pixel, vertical lines, and so this just represents a CCD image. If you want to do it at a very fast rate, you can also do it with CMOS detectors nowadays. So the detection is not difficult. The difficult part is how to get the time information about this radiation. How do you know when the radiation was emitted? To do that, you have to streak this radiation using laser fields, and that is non-trivial when you have such a large bandwidth. Okay, so I didn't talk about attosecond streaking, but that's a whole new topic where you can Google this keyword, attosecond streaking, and that'll tell you how to characterize the time duration of these X-rays.
Yes. I think, Professor Santhu, I would like to share some of our femtosecond laser facilities here in International School of Photonics. I'm happy to state that ours is the first installed femtosecond laser in South India way back in 2003, 2004. Of course, we have some NDR lasers, but we are not having the attosecond pulses generated it. Okay, then even we are working mainly on the laser ablations and nonlinear studies on the high power lasers here.
Yeah.
I think the new generations of the faculty faculty will start the work on pump probing experiments and all these things.
Wonderful. That's great to hear. I mean, congratulations on building this program up. And
yeah. And then let me say it's a wonderful talk, Professor Santhu. That in spite of that you are cold or something very adverse, bad weather condition or so, you have committed your talk in a very nice way. I think the research community here at ISP Cochin University, especially those working in high power lasers, are highly benefited from your highly delightful and knowledgeable talk. Thank you, Professor Santhu, from my behalf and on behalf of all present and from Cochin University of Science and Technology.
Thank you. It was my pleasure. It was great to share this with you.
We would like to thank you, sir. We would like to thank you, sir, for this wonderful talk. I would also like to extend my gratitude to Professor Dr. Mujib for chairing the session. Thank you, sir. Now we are having a short break. The next invited lecture by Dr. Deepa from Kasargod will begin at 11 o'clock, at sharp 11. Thank you.
Okay. Thank you all. Thank you. Bye.